Hello, and welcome to our new unit on Chapter 6. We're going to be working with right triangle trig for pre-calculus. And it's going to be different from geometry. It's going to be the same as geometry, but it's going to also be a little different because we are going to incorporate cosecant, secant, and cotangent. So in our book, this is 6.2. Trigonometry of right triangles. And we're going to have to recall some of our geometry trig portion. Right triangles. Now, as we know, right triangle is a triangle that has one angle that is 90 degrees. So here I'm going to draw a right triangle. I'm going to make a 90-degree angle, and the most important piece to identify in any right triangle is the hypotenuse. This is the most important side to identify. And for the sake of it, I am going to do two colors here. I'm going to call this angle in the bottom right corner alpha, the Greek letter alpha, and then the top left corner, I'm going to call this beta. These are Greek letters that we use typically for angles, like how theta is technically an angle. We use it for angles as a kind of a placeholder. Alpha and beta also are used for angles. So definitely get used to seeing those. Alpha and beta is just for Greek letters for angles. Now, from the alpha perspective, this side that is directly opposite of alpha is the opposite side. And then the bottom side, the base, would be the adjacent side. Adjacent means next to. But if you're looking at this from the beta perspective, this is actually, the base would actually be the opposite side, and the opposite side to alpha is actually the adjacent side to beta. So it's very, very important that we could actually identify these according to the actual angle of reference. If we're looking from alpha, we need to use the proper sides, opposite and adjacent, or versus beta. Okay, so now that we have that settled, we also need to recall our SOHCAHTOA. Hopefully you remember this. I always write it like this as a ratio. SOHCAHTOA, because it actually writes the ratio out for you as opposed to just writing the words out, SOHCAHTOA. And let's go ahead and write these ratios out. Sine of theta. Remember, theta is just a placeholder for any angle. It could be this angle alpha, it could be this angle beta, it doesn't quite matter, but we need to know that sine is always a ratio of the opposite side over the hypotenuse. Cosine of theta is always a ratio of the adjacent side over the hypotenuse. And then the tangent of theta is always a ratio of the opposite side over the adjacent side. And that was our basic trig from geometry. Now that we know what cosecant, secant, and cotangent are, we should also incorporate those. Cosecant of theta is the reciprocal to sine. So you could write it one of two ways. You could write it as 1 over sine theta. But even easier than that, just take this reciprocal. What is the reciprocal to opposite over hypotenuse? Well, it should be hypotenuse over opposite. Wow, that's a terrible hypotenuse. Let's rewrite that. Okay. Secant is technically the reciprocal to 1 over cosine. So you could write it like this, or you could also write it as the reciprocal to adjacent over hypotenuse, which is hypotenuse over adjacent. And last but not least, cotangent, and I'm running out of room. Cotangent can be written a number of different ways. You can write it as 1 over tangent theta, or, and I'm going to write this down here because I ran out of room, you could also write this as the ratio of adjacent over opposite. So these are the things that we need to be able to do, in addition to the sine, cosine, and tangent basic trig. So let's go through an example of this. Let's do a basic one. Example 1. Let's draw a right triangle. Let's make this a nice clean Pythagorean triple, meaning all of the sides in this triangle are whole numbers. 3, 4, 5 is the most common Pythagorean triple, and this is the most basic one. If I asked you, if I said this is our theta, what is the sine of theta? Sine of theta would be opposite over hypotenuse, which makes this 4/5. Cosine of theta would is equal to adjacent over hypotenuse, which is 3/5. And then tangent of theta would be equal to opposite over adjacent, which is 4/3. Now, cosecant of theta can easily be written as the reciprocal to 4/5. What's the reciprocal to 4/5? Well, it's 5/4. I personally would avoid, if you have the ratio already 4/5, it's easier to just take the reciprocal of that, as opposed to writing 1 over 4/5, which requires you to do some keep, change, flip, or multiply by the reciprocal. 1 times 5/4, which is equal to 5/4. I would avoid that if you already have a fraction for sine. If you already have this ratio given, just take the reciprocal. Same thing goes for secant. If cosine's already given, take the reciprocal of it, and you'll get secant, 5/3. And then cotangent, we already have a ratio, which is nice. Take the reciprocal to tangent, 3/4. All right, good. Now, it gets a little harder. Example 2. What happens if you have a ratio that's not, if it just gives you a ratio? So for instance, if, let's say let's say cosine of theta is equal to, let's actually go alpha this time. Cosine of alpha is equal to 3/4. What this means is, we know cosine is adjacent over hypotenuse. So if this is alpha, it doesn't matter which angle you put that in terms of the top left or the bottom right, because we could write this accordingly. 3 is the adjacent side, 4 is the hypotenuse, and we could place those accordingly. 4 is the hypotenuse, 3 is the adjacent side. We don't know what the opposite is, but what if cosine of alpha is 3/4, what is sine of alpha? Well, we don't know what the opposite side is. In order to do sine, we need opposite over hypotenuse. So we actually need to solve for the opposite side. And since this is a right triangle, we could actually solve that using the Pythagorean theorem. A squared plus b squared is equal to c squared, where c is the hypotenuse. So let's do that. We'll call this A, we'll call the opposite side B, we'll call the 4 C, and we'll say 3 squared plus, b squared is equal to 4 squared. 3 squared is 9, b squared stays b squared, 4 squared is 16, subtract 9 from both sides, you get b squared is equal to 7. You need to isolate the b. Squares and square roots cancel. You get a plus and a minus in front of the square root, and b is equal to only a positive 7 because lengths cannot be negative. Like in geometry, a length can never be negative. So we keep this as a positive root 7. So that means I'm going to put here root 7 as the opposite side. Now we could actually solve for sine of alpha. It's going to be opposite side, root 7, over hypotenuse, 4. And now we have a solution. All right? So the last part to this part 1 of this lesson, this is going to be a part 1, is going to be working with special right triangles. Now, this is something we kind of just more so have to memorize for now. And it involves the 30, 60, 90 and 45, 45, 90. So, in a, let's call this first one 45, 45, 90. Because this is the easier of the two. So 45 45, 90 refers to the angle measures of this right triangle. That means both angles that are not the 90-degree angle are congruent to each other. They are both 45 degrees. Okay? And what happens here, let's do this, is this. If you remember, if you recall from geometry, anytime you have angles that are congruent, that means you have sides that are congruent in a triangle. This is technically an isosceles triangle, which means these two sides are actually congruent to each other. The question then becomes, how do you solve for that length? Well, this is the fun part. If I said this had a length of 1 and a 1, let's put this actually in blue, we could actually solve for this, correct? Because we have 2 out of the 3 sides. So we could do technically the Pythagorean theorem. We could say 1 squared plus 1 squared is equal to, let's call this c squared. 1 squared is 1 plus 1 is equal to c squared. 1 plus 1 is 2, it's equal to c squared. Square root both sides. And we get c is equal to the square, it's like if there's a plus minus, but the minus obviously doesn't matter because the lengths can't be negative, square root of 2. Now, if, for instance, I'm going to do this in pink, let's say it was like the unit circle where the radius was 1, right? If we have a unit circle here, we would have that's a terrible circle, but hopefully you get the idea. This is the center of the circle, this is the end point, and the radius is 1, so that means this hypotenuse is equal to 1. Well, what happens here is this. The length of these sides are congruent to each other, and you could use the Pythagorean theorem to solve this as well. Because since these are equal to each other, you could call them x. You have x squared plus x squared is equal to 1. You get 2x squared because x squared plus x squared is equal to 2x squared. You add the coefficients. You get 2x squared is equal to 1 divided by 2 to start getting the x by itself. X squared is equal to 1/2. You square root both sides, and guess what you get? X is equal to, when you simplify this, this should become root 2 over 2, the positive version of it. And isn't that the coordinate that we have in the unit circle? Positive root 2 over 2, comma, root 2 over 2. So just like the unit circle, we actually end up with this coordinate. Now, what happens here particularly is more commonly we'll see this version of it. If we have 1, 1 as the sides, then we'll see root 2 as the hypotenuse. And it's not obvious, but we can multiply by some coefficient or some variable. If I said 1 times a, this would be multiplied by a, this would be multiplied by a, and then you get a new value. For instance, if a is equal to 3, then the lengths would be 3, because 1 times 3 is 3, 1 times 3 is 3, and this would be 3 root 2. If you don't believe me, try this out. Try this out. 3 squared plus 3 squared is equal to blank, c squared, and see what you get. Okay? So that's a 45, 45, 90. It's always going to be some increment of 1, 1, root 2. All right. Last part to this. First part, anyway. Delete that. All right. 45, 45, 90 is always going to be some version of this. 1a, 1a, root 2, a. Okay. 45, 30, 60, 90. So if you could take my word for this aspect of it, 1a, 1a, root 2a, 30, 60, 90 follows the same logic. Okay? Ooh, let me erase this because that's an eyesore. Let's flip this around just so it makes it a little bit different. Okay. We have a right triangle. We're going to call this a 30, 60, 90, pertaining to the angles. This top one looks more so like it's 60 degrees. This bottom right one looks like it's 30 degrees. And there is a ratio that actually happens here. If we have a length of 1, for instance, starting at opposite of the 30 degrees, the nice part about this is the hypotenuse will always be equal to 2, double that. and then the last side will actually be root 3. This will always be the case. So if you want to, this is personally what I would do. I would call this A, in terms of side lengths, opposite side, and then the hypotenuse side is going to be A root 2. That is always going to be this case for 45, 45, 90. 30, 60, 90 is slightly different. If you call this B, because we're using a different triangle, the opposite of the so this opposite of the 30 will be B, the B side. The hypotenuse will be the 2B side, so this is going to be always twice that length. And then this is always going to be B root 3, the 60-degree side. This is always going to be B root 3. Okay? And this is the last part to the 30, 60, 90. All right. So with that said, this is the end of part 1. This is what we need to know for the basics of right triangle trig. Okay? If you do have any questions, please ask, and I'll see you in part 2. Have a good one. Bye.